Let's continue with our big example. In this case, what we will do is we will set a benchmark example to do some simple operations. In this case, what we do is we define a data structure for vectors where we have we have a structure which stores the length of the vector and the pointer to the data, and this is defined as array. And the data type here is we will use them to we will differ them like an int, long, float, or double, because we have to check the performance uh, of our program under different data types. And we defined a function which is called get vector element, okay, to retrieve the element stored at basically to retrieve the vector element and store it at val. So it takes the vector, okay, which is pointing to here. It says the index, which element that you want, and this is where it stores the result. So when it gets the index, it checks against the VLAN. Okay, if it's true, then it returns v data index here, and then does this. And here's the computation that we are interested here. That we, now it's called combine. It combines the sum of the sum or product of vector elements. So when we have all these elements here, and it either does a sum of all of them or a product of all the elements. And this is done as follows. So you get the vector pointer, okay, and this is where we will store the result. We initialize it with the identity. This identity can be 0 if it's an addition. It will be a 1 in the case of multiplication. And we essentially have this loop from I to vec length, which returns the value, and then I plus plus. And then we define our local variable here. We define a val here to get the result here. And we say I'm accessing the vector v with this index and to put the result in the val. And then since this will be our destination, it will be destination op val, where op will be plus or multiplication. And remember that this data type that I'm talking is, it can be int, long, float, or double. Now, before we move on, let's talk about the time scale. Of course, when we are measuring time, typically we use nanoseconds, which is 10 to the power minus 9 seconds. Okay, this is usually the time scale, and it relates with our clock cycles, where it's if you have, for example, a 2 gigahertz clock cycle, it means that you have 2 times 10 to the power 9 cycles per second with a clock period of 0.5 nanoseconds. So this is useful for absolute measurement, but in this case, related with your computation complexity in algorithms, we will be having we will define a metric called cycles per element. It's essentially saying how many cycles do I spend to process one element in the system. Okay, so this expresses the performance of the program that operates on these vectors or lengths. So what you do is you have the length of the data as n, okay, and in our case, basically the cycles per element is basically cycles per operation, okay, and typically the time that it takes is cycles per element times n, which is the number of, plus some overhead. This overhead is due to the loop constructs, because we have to, when we are doing this operation, when we are combining, say, adding all the numbers in the vector, we also on the side have to increment the loop variable and compare them, etc., etc. Okay, so that gives us an overhead. So here is basically what we would see. Like this is the number of elements that we have here. And these are the number of cycles, and we will share code, especially for the fourth assignment, how you can measure the number of cycles. And you can see that you can have when you plot this, like depending, then you have this certain bias. This is the overhead, And then we have these different loops here, different lines that's with different slopes here. Okay, so you can, and this slope essentially defines the cycles per element. So let's define basically our initial basically benchmark, and in this case again this is the what we have seen so far. And what we'll do is that we will look at the integers and the double floating points, and we'll look at the operations, the integer addition, integer multiplication, double addition, and double multiplication. So when we do this when we run combine one with no optimization at all, then we get in addition 22 cycles per element. This is essentially these are the CPEs, okay, that we measure. In multiplication, it will be 20 cycles per element. Double, it's 1995, and multiplication 20. So they are roughly the same. You just kind of like you may say, well, I'm surprised because addition is usually cheaper, right? And then when we do this with O1 optimization, then it drops half. So we will see that, at our initial base, the benchmark is that we have this CPE is actually 20. Okay, 20 cycles per element. How low can we go? Any guesses? Well, believe it or not, we will go at least up to 80 times faster than this, which will be, you should get curious how we do this. So with this, we do the basic optimizations, the machine-independent versions, right? The first, let's look at this code, okay? The first thing that you can realize is that this vector length here, when we can move up, it's code motion, right? That's basically it's code motion. And the second thing, this we have learned, and the second thing that we have learned is that instead of accessing the destination here, declare a local variable, let's call them like t, and then declare a local variable of say, data type t here, temporary, and then accumulate the partial result in here, and then finally at the end write it back to that. So this is the code that I'm talking about. So the first thing is we complete the vector length here, and then in the loop, and we use this because this value will not change. So this is code motion. And then what we do is we declared a variable, temporary variable here, t, we initialized with identity, and then we operated on that, and only out of the loop we assign this into the destination, right? And when we were working with the vectors, when we were getting this excess elements, we get the start here. And what we would do is, once we get this, then we just access it with DI. So when we do this, you will be amazed that this is called combine 4. Now, all of a sudden, my cycles per element drops 1.27 here. 3 to multiplication, 3 in addition, the floating point, and 5 with floating point multiplication. Okay, so this is really, really nice. You can say that, oh, that's the end of the story. No, I cannot go beyond this. This looks really, really good. But guess what? We have more tricks up our sleeve.